Section 8.2, inverse variation. The objective in inverse variation is to define and solve problems that involve inverse and joint variation. So we start with our equation y equals k over x. And the reason we write it this way is because these variables y and x are inversely related to one another. In the previous lesson we wrote y equals kx because y and x were directly related to one another. Now what we can see here is this. As the value of x increases, it means that the denominator is increasing. As a result, this overall fraction will be decreasing. So as x increases, y decreases. And we can see that here clearly in this graph. As the value of x continues to increase to the right, we'll see the value of y drops. It decreases. And what we'll notice is, if we solve for k here, we get k equals the product of x and y. And we'll notice here that 1 times 1 is 1. 2 times 1/2 is 1. 1/2 times 2 is 1. So the product anywhere along this curve of the coordinates x and y is always equal to some constant value. In this graph, this happens to be the graph of y equals 1 over x. So the product happens to be 1. When we solve for this, we get xy equals 1. And you'll notice that every product along the way is indeed 1. Now k again is called the constant of variation here. One obvious application of this is the formula that we've already studied, which is d equals rt. So we'll see here that if we think about a certain distance d when we travel to school, if we travel at a faster rate, what happens is the time decreases. So what we'll do here is we'll take a look and say to ourselves, well, if we solve for r, we get r equals d over t. Well, this variable here we'll say is a constant, right? This is the same distance no matter what. It's not changing, the distance from home to school. But if I increase the rate, what will happen as a result of that is I'll end up decreasing the time here, because these two variables are inversely related. So as the rate of the speed at which you walk increases, the time it takes has to decrease, and vice versa. If the time it took increased, it means you're walking at a slower rate. So if this increases, then your rate ends up decreasing again because this is a fixed quantity. So example 1 says that if c is inversely proportional to d, so right away start by writing this. C is inversely proportional to d. And that's my statement. Again, c is, this part means inversely proportional to d. So we put d in the denominator. When c is 2, d is 3.6. So find out the following. So right away we know this information, so let's use it to find out what k is, our constant of proportionality. Or constant of variation in this case. So we solve for k, we multiply by 3.6 on both sides. K turns out to be 7.2. So now what we have is, instead of our generic equation here, we have a specific equation which relates to the given scenario in the problem. So now we can use this equation to figure out the following parts a and b. So we want to find variable c when d is 4.5. So c is already solved for. So to do that for part a, we could just plug in 4.5 here. So c equals 7.2 over 4.5, which is 1.6. But for part b, we're going to solve for variable d when we're given c. So let's go ahead and take this equation here and solve it for d. To do so, all we need to do is switch d and c. So multiply by d and divide by c. Do it all in one step. d equals 7.2 over c. And now we're given the c value of 6.4, and we're told to find d. So let's plug in 6.4 here. And we get a value of 1.125. Example 2 says, for cones of equal volume, the height is inversely proportional. The height is inversely proportional to the square of the radius. So to r squared now instead of just r of the base, as the base radius. If the radius of the cone is 10 centimeters and the height is 15, alright, so right away, height is 15, base or the radius is 10, we'll solve for k here. So multiplying by 10 squared or multiplying by 100, we get k equals 1500. So if K equals 1500, we can write our specific equation, H equals 1500 over R squared. And now what we're going to do is, for a cone of the same volume, right, equal volume, that was the whole idea, equal volume, we'll have a height of 60, we can determine what the radius is. So we have to solve for the radius here. So solving for R, let's switch R squared and H, and then take the square root. Now I'm only going to write the positive root because I know I'm looking for a radius, which is a length, and as a result I don't care about the negative root here. So the height of the cone is 60 centimeters, so we can solve for the radius. So we have 1500 over 60. Cancel those last zeros. 150 over 6 is really 25, so this is radical 25, or 5 centimeters as a radius length. And this makes sense, okay, because the height went up, the radius went down from the previous scenario there. Now if we look at direct and inverse variation together, we call it joint variation. And we can say that many important physical laws combine these types of variation. For example, Newton's law of gravitation says that the force of attraction between two spherical bodies is directly proportional to their masses, so K, M1, M2, but it's inversely proportional to the square of the distance between their centers, R. So inversely proportional to R squared. So what we can really always say is this. If something is directly proportional or directly related, it ends up in the numerator as a product. If it's inversely proportional or inversely related, it ends up in the denominator, and it looks like division here. And this happens to be the square of the distance, so that's R squared. So this is our Newton's gravitational law. Turns out that Newton's gravitational law really looks like this, where big G is used to represent the gravitational constant throughout the whole universe. So G M1 M2 over R squared. Example 3 says the electric field produced by a charged particle varies directly with the charge on the particle. So the electric field E varies directly with the charge Q on the particle, and inversely as the square of the distance from the charge itself. Now we're told that on a planet galaxies away, the electric field felt at a distance of 13 meters, so R is 13, from a charge is, so the electric field at a distance of 13 meters from a charge is 25 newtons per coulomb. When the charge on the particle producing the field is 8 coulombs. Determine the charge that would produce a field of 18 newtons per coulomb at a distance of 11 meters. So given this information, let's find our value of K. So solving for K, we get E R squared over Q equals K. And plugging in, we have E times R squared all over Q, giving us a value of 528. Now, that's our constant, so that's going to be our new equation. Our specific equation will be used here. 528Q over R squared. Now the question says, determine the charge, so find Q, if the field is 18 newtons per coulomb and the distance away is 11 meters. So determine Q, so let's solve for Q here. So we get ER squared over 528, that's what Q equals. If we plug in for E and R squared, E is 18 newtons per coulomb, R was 11, so that's 11 squared over 528. That gives us the charge necessary to produce that field. And that charge is 4.125 coulombs. Make sure to use your units to help you in these problems. Finally, example 4 says the period of oscillations of a mass, so the period P of oscillations of a mass moving in simple harmonic motion is proportional, so we'll use K to start, to the square root of the mass M, so radical M, that's how we write proportional to the square root of M, and inversely related to the square root of the spring stiffness K. Well, that's going to be a problem. We can't have two K's here. So let's change this K and write a random dummy variable, any variable, call it, say for this case, C. So that's now our constant of proportionality, C, because K was used as a parameter in the problem for the spring stiffness. So we can't use it as our constant of variation as well. We're told that the period of oscillations is 9.2 seconds when the mass is 150 grams and the spring stiffness is 70 newtons per meter. So first, let's plug in those numbers to find our constant of variation. We can solve for our constant of variation by writing this as P radical K over radical M equals C. Plugging in for these three variables, though, P is 9.2, radical K is radical 70 over radical 150. This gives us a value of 6.28, and that should ring a bell. That happens to be double pi. So that's our constant of proportionality in these equations. So P equals 6.28 root M over root K. And in physics, it happens to be 2 pi in front of this as a constant of variation here. So this is exactly what we want to get. Now, we're told that the scenario says, what would the mass be to produce an oscillation of 15 seconds if the spring stiffness is 40 newtons per meter? So we have to solve for mass here. So P radical K over 6.28 is equal to the square root of M if we solve for the square root of M. But we want to get M, so let's square this entire thing. P squared, and now the radical K squared just simply becomes K. Remember, squaring every term over 6.28 squared, and that equals M. To see that, take a look up here. That's what we're doing. Okay? So we have to distribute the square to every term because this is a product. These are all factors. So this is what we get as a result. We're told that the spring stiffness in this problem happens to be a value of 40. So that goes in here. The period is 15 seconds. That goes here. All over 6.28 squared, giving us the mass, a value of 228 kilograms.